I just want to welcome everyone to our webinar about the hard facts about confidential computing. My name is Linda Popky. I'll be your moderator. Just want to introduce the Confidential Computing Consortium. This is a community focused on open source licensed projects, securing data in use, accelerating the adoption of confidential computing through open collaboration. Every member is welcome. Every project meeting our criteria is welcome. We are a transparent and collaborative community, and we as members, contributors, and leaders pledge to make participation in our community a harassment-free experience for everyone. So I'm going to introduce today's panelists. Again, I'm Linda Popky. I'm the moderator. I'm with Anjuna Security, and we are a software provider providing confidential clouds in the confidential computing space. Our panelists today are Mike Ferron-Jones from Intel and Mark Knight from ARM. So let me introduce each of the panelists. First, Mark has worked for more than 30 years in the development of technology products. He has over 20 years specializing in security and cryptography. Before joining ARM, he held product management responsibilities for security products at Encipher, Thales, Microsoft, and Grosvenor Technology. At ARM, he is a director of product management within the Architecture and Technology Group, and he's responsible for security architectures, including the ARM Confidential Computing Architecture announced in March 2021. Okay, welcome, Mark. Mike is the Director of Data Center Security Marketing at Intel. He is a technology industry veteran with over 30 years experience in data center and client segments. He's responsible for customer engagement and go-to-market on confidential computing, crypto acceleration, and infrastructure integrity technologies on Intel Xeon platforms. So welcome. I'm going to stop sharing the slides and we're going to get started here. We're going to be going through a number of questions and talking to these panelists about what hardware role there is in confidential computing. If you have questions, please put them into the chat or the Q&A and we will try to get to them later. So we're going to start out by asking, what is confidential computing and why is it so important? So Mark, do you want to start out with that one for us?
Yeah, that's great. Thanks, Linda. So confidential computing is really a model for general purpose computing where the platform and the workload, and when I say workload, I mean the combination of code and data, is attestable. I'm sure we'll come on to that later. And also workloads are provably isolated from the underlying platform and adjacent workloads. Ultimately, that means a smaller attack surface and less has to be trusted, whether that's unseen code, administrators, neighboring workloads, and other tenants sharing the platform. So I think you said, why is it important? So I expect confidential computing to become really a standard approach for protecting data in use. The principle of using secure enclaves is not new, but confidential compute, I think it really democratizes secure computing by making secure, virtualizable computing available to all. And I think as an industry, that has the potential to unlock significant cost savings and energy savings for users, all users of compute. Whilst I think simultaneously allowing more data to be shared and that data and the code to be more strongly protected from the ever-growing security threats.
Mike, you want to add anything to that?
Sure, thanks, Linda. I think to add to what Mark said is that the industry is really familiar with data security for data that is in flight or data that's at rest. So data at rest, we use disk encryption, and we make sure our stored data is encrypted and protected while it's at rest. We use network encryption, TLS, HTTPS, all of the acronyms that define data that's encrypted over networks. It's just that historically we've had a gap in the data chain, that when that data is in active use in the processor, it's now it has historically been unencrypted and available to be intercepted. So confidential computing is designed to close that remaining gap and make sure that whether data is at rest, in flight, or in use, it is protected from end to end.
So tell me, why is hardware so integral? Can't you isolate and protect data in software? Mike, let's start with you.
Sure. I think for me, what it comes down to is that with all software-based security, there's always something below you that can undermine your security. So if you're running at the application level, there's a hypervisor. If you're running in the operating system, or if you're running in the operating system, there's a hypervisor below you, or even things like firmware-based attacks. All of these things are potential vectors to get underneath software-based security. Hardware's at the bottom of the stack, and so it gives you a much more immutable defense against attacks and vulnerabilities higher up the stack.
So, okay, so there's a lot of different things we've heard about. Can you talk to us about the difference between TPM and SE and TEE? And Mark, do you want to start with that one?
Okay, so I think really it's about scale. Trusted platform modules and secure elements are types of dedicated security processors, and I think they're really great for protecting small algorithms, cryptographic keys, roots of trust. But typically they can be too constrained to really protect mainstream workloads, perhaps memory and processor intensive workloads. So confidential computing is really a model for secure computing where workloads can run within a hardware-based trusted execution environment, but instead of running within that more constrained environment, such as a secure element, they're running really on a high-performance application processor. And trusted execution environments, they can come in a variety of sizes. Some of them can support confidential compute, whilst I think really others are more suited for more limited applications. So it's really about scale.
Okay, Mike, anything to add to that?
Yeah, and just to add a little bit to what Mark said is that TPMs and SEs, are limited function devices. They're very important, but they're limited. When you think about confidential computing, you got to think about having the full capabilities of a fully functional server or computer at your disposal. So, in general, whatever you can do on a general function computer, you can do in a confidential computing trusted execution environment. So SEs and TPMs may provide important services to creating Ts, but they're not equivalents to each other.
Okay, so we often hear the term trusted space or trusted boundary associated with confidential computing. So how is this related to an enclave and why is it important? So Mark, tell us about that.
Yeah, so with confidential computing, workloads run within an enclave that's really designed to run an unmodified operating system or an unmodified virtual machine. And the trust boundary really needs to tightly envelop that workload as tightly as possible. And I think the goal really is to include the absolute minimum of additional system code that isn't part of the workload within that trust boundary. Now, the code outside of that enclave, outside of that environment, I call that the trusted computing base. And really the goal is to minimize the size of that trusted computing base. So minimizing the quantity, the volume of privileged software and firmware that the workloads running within the enclave need to trust.
Mike, anything to add to that?
Yeah, just a little bit to expand on what Mark said is that different vendors are going to use different names for the trust boundary. Sometimes we always call it an enclave, like in SGX, Intel SGX terminology, we use the term enclave. Others might use words like realms or trust domains or other type of words, but they're all essentially referring to the same concept, which is what is the perimeter around the software that has privileged access to data and that you need to be able to trust, and then the software that's outside that boundary that does not have privileged data access and that you don't need to trust. Now, one of the things that I often see these perplexed looks on folks' faces when we talk about trust boundary, because as Mark was mentioning, you want your trust boundary to be very, very small. And everybody's like, wait, I want to have a large trust boundary. Trust is good. Well, not in this case. You want to have as little code as required to have privileged data access. As much as you can freeze out of the trust boundary that doesn't have access to your privileged data, then that is better. You're going to have a higher level of security if you have the smallest possible trust boundary.
Okay, so we're talking about trust boundaries and small and large, et cetera. And then there's this concept of attestation. So how does that relate to here and why is it important? So Mike, why don't you start with that one?
Well, reliable attestation is incredibly important. And what it means, it's the ability of a user of a trusted execution environment to be, cryptographically or reliably assured that what they are expecting to be in their trusted execution environment is exactly what they expect it to be. And that environment has come up into a known reliable state. So this is especially important in, say, the public cloud when you're using trusted execution services through a public cloud. You don't have control over the infrastructure. So you have to be able to have a reliable means to be able to query that T and find out, is it genuine? Is it running on the correct hardware? And has the software that's loaded into that trusted execution environment matched exactly my expectations? And there's a number, each of the different vendors and services have a slightly different way of doing it, but they're all designed to do essentially that same thing. Mark, do you want to add anything more to that?
Yeah, I think that's great. Thanks, Mike. So yeah, I think we're aligned. Attestation is absolutely central to the value proposition of confidential computing. Attestation records for the platform a workload is running on. Also, attestation reports for the workload itself. Those reports can be presented to relying parties who want to verify the integrity and trustworthiness of the workload and the platform it's running on. Attestation reports will typically include information like the version of the hardware, any firmware components, trusted software components, which we've talked about minimizing, but there will still be some. So you need to make sure that they are the versions you expect and that they're as small as possible. And indeed, the configuration of the platform is important. And I think the other key element is considering the relying parties that ultimately receive attestation reports. They need to be able to verify those reports in a very standard way. And I think interoperability between different implementations of confidential computing, that's where it really comes together in ensuring that any party is able to recognize and evaluate those attestation reports. So this is one place where in ARM we've been working really closely with the Confidential Compute Consortium in terms of initiating and now really starting the transfer of a project we've started called Project Ferron. And Project Ferron is really a framework that can allow anybody to build and run an attestation verification service.
Okay, so this is all very nice. It sounds great, but it's all still theoretical. So are there use cases we can talk about that show exactly how attestation and TEs and all of that gets used? So, so Mark, can you give us kind of an example of a good use case where attestation would be important?
Yeah, so I think one of the first major uses, I think, for confidential computing in general is the continued migration from on-premise to the cloud. And there are a lot of workloads that have not yet migrated to the cloud. If you think about financial services, healthcare, in some of these segments, as much as 90% of workloads are still actually running in private data centers. So if you think about the reasons why organizations want to move to the public cloud, of course, there's the reduced power, there's the reduced reduced cost, the greater efficiency. But then you're talking about running your application, having your code and your data in a data center that you're not going to see, and that you're having to trust somebody else to run on your behalf. And that has historically been the barrier to some of those segments in some cases. So really, attestation is a way of having your eyes in a third-party data center, where when that workload is moving into, for example, the public cloud, you can actually, before you allow keys to be released into the workload that may allow your data to be accessed and decrypted, you can have a really strong verification that the system and the configuration of that system in the cloud is exactly the way you expect it to be. And that really gives you that control point, not just when you first migrate a workload into that off-premise environment, but every single time that workload runs. So it's a continual process, which I think is part of the great strength of attestation.
So that gives us a great example of attestation. Mike, what other use cases? How about something around multi-party applications?
Yeah, thanks, Linda. So some of the things that we're seeing on the Intel side is some of the earliest adopters of confidential computing are customers that that they know that they could benefit from being able to collaborate or have create services that involve multiple parties, but the data that they need to share is either highly regulated or highly proprietary. And although they would benefit from pooling that data to create some kind of a shared analysis, they either by law or just by good business practice, don't want to expose that data to the other parties. And that's one of the ways that confidential computing is really taking off in certain segments where, say, for example, you want to train an AI model, or you get the inferences from a shared AI model that's been trained across multiple different organizations' data. It's not just trained against your small data set, but also against the whole data set of a much larger community of inputs. And you couldn't just take a whole bunch of personally identifiable medical information and throw it into a common pool. It would be illegal and unethical. But using confidential computing, that data can travel from the different institutions that are contributing to the analysis. It can be encrypted, over the wire. It can be encrypted in storage, and now with confidential computing, it can be encrypted in use. So none of the parties can see it while that data is being used to train the AI model or benefit from its more informed inferences. We're seeing this in industries such as healthcare, as I mentioned, financial services with things like anti-fraud and anti-money laundering, which never occurs just within one bank. It's one of those, in order to recognize the pattern, you have to be able to look across multiple institutions. And confidential computing gives you the ability to collaborate while keeping your data confidential. Some other places that we're seeing it are, as Mark talked about, was just cloud migration. Customers that want to take advantage of the economics and flexibility of public cloud, but are reluctant to send confidential data there. One of the great things about confidential computing is not only does it provide a higher level of security for the data, it draws that trust boundary that we were talking about around your software and your data, so that not even your cloud provider has access to that data. So I can host my data in a cloud provider, but that cloud provider's cloud stack, their hypervisor, their system admins are all outside the trust boundary and don't have data access. And then just, finally, some of the other places we're seeing are kind of traditional high security applications, things like software HSMs, hardware security modules, where you're protecting and managing, encryption keys across multiple applications or clouds, government applications where you're working with highly confidential, highly sensitive data. All of those things are opportunities to increase the level of security and privacy with confidential computing.
So we could use confidential computing across multiple clouds. You talked about migrating to the clouds. We can use it on premises as well as within the cloud. Do you want to talk a little bit about that?
Sure. So yeah, I think you can consume confidential computing anytime that you can get platforms equipped with processors that include, confidential computing capabilities. Being from Intel, that means, if you're able to get, say, like third generation Intel Xeon scalable processors, either via a cloud provider or one of your leading OEMs, folks like HPE, Dell, Lenovo, all of those folks are providing servers today that have Intel SGX capabilities. And so you can build your own confidential computing environment on-prem if you wanted to, or you can consume it through one of the cloud providers that's also equipped with those platforms.
Mark, anything to add to that one?
Yeah, so I think, in the first instance, I expect confidential compute to be used in the public cloud and private data centers. However, really, I think of confidential compute as being the next step in the journey towards virtualization-based security. And that's a technology we already see on things like our laptops. Virtualization itself is increasingly being used in automotive segments, in mobile, consumer electronics, edge gateways. So I expect in time, confidential compute will propagate to those applications too, and help to strengthen the protections offered by that virtualization-based security.
So is this available today? Mark, is this something that's coming in the future, or if I'm interested, could I use it today?
Yeah, so there are platforms offering confidential compute today, and there are a raft of innovations coming downstream. At ARM, we announced our confidential compute architecture last year, and we expect that to be available in silicon in the next 2 to 3 years. And that's really going to strengthen the protections that are available in the market today.
Mike?
Yeah, and again, like Mark said, a number of different vendors are providing confidential computing solutions today. At Intel, we of course have Intel SGX, our software guard extensions technologies. We've been shipping that for a while. We've announced an additional technology that's going to be coming up in a future Xeon processor. It's called trust domain extensions, or TDX. And then other companies that are part of the consortium, such as AMD, also have their own technologies that are shipping today. So yeah, if a customer is interested in taking advantage of confidential computing today, they have their choices right now of deciding whether or not they want to purchase services with confidential computing capabilities and building it in-house, or going out to one of the public cloud providers that's offering confidential computing services, such as which you're finding it like Microsoft, Azure, OVH, IBM, other cloud providers.
Okay, so I have to ask you, because it's been reported in the press several places that Intel is dropping SGX. So can you talk to that a little bit?
Okay, yeah. And so Intel has removed SGX from our client processors. So Intel Core microprocessors that are designed for the PC ecosystem. So for those processors, yes, they removed SGX from that capability in order to focus on other areas of security that were more aligned to where the PC ecosystem was going. On the data center side, Intel Xeon side, SGX is going strong, and it is on our roadmap for the foreseeable horizon. And we are 100% behind SGX in the data center processors. So the confusion that caused on the client side is unfortunate, but I just want to be super clear. Investing in SGX in the data center is a reliable bet.
Okay. So Mark, tell me, does confidential computing use homomorphic encryption? And wouldn't that be the most secure way to protect data in use?
Yeah, so homomorphic encryption, that's one of the sort of frequently asked questions around confidential computing. So that's a great technology, but it's really quite limited in terms of its utility today. So homomorphic encryption is around being able to process data without decrypting it. So you can perform some limited math operations on data in that state at the moment. But if you think about the mass of existing applications that people need to run, that it isn't really possible to rewrite those using using homomorphic techniques. That makes homomorphic encryption really a much more niche proposition. And what we're really trying to do with confidential computing is have a mainstream proposition where any application, any workload, existing software can be migrated to run within a much more secure platform, really without having to modify the existing application. So that's really the key difference.
Mike, anything to add to that?
Yeah, I think there's, and this is homomorphic is a really exciting area of research that Intel and many other companies are investing in. It is likely a ways away from mainstream use, largely because of the performance that it currently yields on today's microprocessors. There's some specialized hardware, purpose-built accelerators that folks are investing in, including Intel, that could eventually bring this to more mainstream adoption. But right now, today, it's really in kind of its early stages. We do have, Intel does make some software toolkits, our Intel HE toolkit that allows people to do some interesting research and POCs using homomorphic encryption. But for most workloads today, if you're looking at doing protection in use, confidential computing is going to be the one that gives you the most availability in terms of actual hardware choices today, and give you the best performance for the applications while maintaining a really high level of security.
Okay, so that makes sense. But what's the impact on performance of confidential computing? Are things going to slow down?
It depends. What we've seen in general on SGX is that an application could from running in a completely unencrypted state to running in a confidential computing state, it could see 10 or 15% performance drop. Now that can be reduced with additional optimizations. One of the biggest things that causes performance impact is how often you're going in and out of the trust boundary. In the case of SGX, it's going inside and outside the enclave. So the fewer times that the way you design the software is to minimize the number of trips across the trust boundary. And the fewer trips across the trust boundary that you can create in the software processes, the higher the performance will be and the closer it will be to native performance.
Okay, Mark, anything?
Yeah, I think that's a really good answer. So, yeah, of course, the goal of confidential computing is to provide strong security without impacting performance. At ARM, we've had the trust zone technology that's been in the market since around 2003, and that's a similar concept, albeit on a slightly smaller scale, that's been accessible primarily to OEMs developing products, not necessarily end users, but that's allowed developers to run code within a secure enclave on their main application processor. That's really had a negligible impact on performance. And really, I think for most users, I expect the performance impact of confidential computing to also be minimal. Where there is increasing complexity, that can be mitigated. There are some operations that are more expensive. So, for example, potentially starting up a virtual machine, something like that. But some of these operations are relatively infrequent, or it can be mitigated with additional hardware in the design process.
Okay.
And Linda, I'm sorry, just one last thing I want to add on that is that the trade-off in terms of security versus performance. I mean, a lot of people, if you tell somebody like, I don't want to take a 15% performance hit on anything, that's ridiculous. But you got to remember what the design goal is. The design goal here is to dramatically increase the security around the data and the confidentiality and privacy. So one, you might want to weigh the performance implications versus, what is the fine or the reputational damage of a data breach? The second thing is that in the cases of some of those things like multi-party compute that we were talking about before, you're now getting the higher level of security in a thing that you might not have even been able to do legally or ethically before, because you're able to now collaborate on confidential data without exposing it to the other parties. That may have either been impossible, or it would have involved extensive days or months of data sanitizing and anonymization. So when customers are looking at it, they should take a look at both sides of the scale. What is the performance impact against? What is the security upside? And what are the new capabilities that are being enabled by confidential computing?
Okay, so I've got a question from the audience. What types of attacks does confidential computing protect against? So Mark, do you want to start with that one?
Yeah, maybe I'll have a go at turning this question around. Thanks for the question. And looking at the types of attack it doesn't protect against. So I think if you look at the workload running within a confidential compute environment, you still have to trust that workload with your data. So really what you are doing is thinking of your workload as an island. You have to trust what's on the island. Everything outside of that, you dramatically reduce the trust you have to have in that code. Now, whether that's an adjacent workload that could be another department within your organization or another tenant entirely, you no longer have to rely on the good behavior of that external code as much, but you do still have to trust the code that's in your workload. Of course, one thing that helps you there is attestation, in that if that workload is changed in any way, shape or form, then you can detect that much more readily. So if an attacker tries to change your workload, change your code, some sort of injection attack or malware, then it's going to be much easier to detect that. Anything you'd like to add, Mike?
Yeah, I think just the different types of attacks are also often related to that idea of the trust boundary too. So the smaller the trust boundary, the more different types of attacks that can be mitigated by it. So if, for example, your trust boundary is drawn around a virtual machine, everything inside that virtual machine potentially has access to privileged data. So that could include the guest operating system and any vulnerabilities in the guest operating system. Any other applications that are inside that VM could potentially have data access. If the trust boundary is drawn even smaller, if it's around a container or a application or even a particular process within an application, then the number of vulnerabilities that you're potentially exposed to continues to shrink. The trade-off with that, for most folks, is that as you shrink that trust boundary, you often have to do more and more software adaptation to designs specifically for that environment. If you have a VM level trust boundary, oftentimes you're able to just drag and drop existing applications into that environment, but you don't necessarily have the same small trust boundary and level of protection that you would otherwise.
Okay, great. So if I wanted to do something, if I'm a developer and I wanted to do something now to get ready or start working in confidential computing, where would I go? Mike, we'll start with you on that one.
A couple different resources. At software.intel.com, we have a number of different SDKs for developers who are designing from the ground up. But I would say that your fastest path to confidential computing in an Intel environment is to go to one of the enabled ISVs. This includes folks like Anjuna, Fortanix, Edgeless Systems, other folks that are designing solutions today built around Intel SGX. And so no matter your use case or your industry, there's usually an ISV that is interested in or that's available today to bring solutions to you and get you up and running as quickly as possible. Other things to take a look at: if you are looking at you have your own proprietary applications and you want to get them into an environment, you can look at things like library OSs, some of which are available from ISVs. Others are open source, like Grameen, that allows you to take an existing application and start running it into an SGX enclave without any modifications. So those are some of the faster paths to being able to take advantage of it. You don't have to build confidential computing from scratch. You can work with either a software provider or software tools to bring applications in pretty quickly.
Mark, anything to add to that?
Yeah, thanks. So certainly please do take a look at arm.com/armcca, where we have a wealth of resources. As we've mentioned a couple of times, attestation is really key to confidential compute. The compute element is going to be largely transparent. So if you look at any of the confidential compute platforms available in the cloud today, that's going to be a very easy migration as those platforms get updated and enhanced in the future. But definitely do look at attestation, because to really take full advantage of the power of confidential compute, you need to be thinking about how different services are going to measure and attest each other and obtain the trust. So you're confident in sharing data between services, between different vendors, between different classes of device. Definitely do take a look at Project Verizon, which I mentioned is software that you can use to help you build attestation verification services. And of course, finally, don't forget to join the Confidential Compute Consortium.
Yeah, I'm glad you went there, Mark. I just want to say that all the vendors, many of the vendors that we're talking about that have solutions across multiple hardware platforms, are members of the consortium. So check out the members and their profiles, and that's a great resource to be able to find companies that are able to provide solutions for you.
Great. So I have to ask, because you two are competitors in the marketplace, but everything you said today, you seem to be pretty much in lockstep. So why is that? So Mark, let's start with you. Why do you think that the two of you who are out competing in the marketplace are in so much agreement here about confidential computing?
Yeah, so I think confidential computing is more of a model or a paradigm for computing than a particular technology. And as we have discussed, the technologies will continue to evolve. Different vendors have, different approaches. I think for the widest number of workloads to benefit from confidential compute, it's really important that different implementations can work together. For example, workloads on platforms should be mutually attestable. And relying parties in any environment should be able to recognize and verify attestation reports from other devices. And I think we really achieve that best by working together. And I think generally, if you just look at the sort of IT security industry, you'll find that vendors, put the need to deliver secure platforms and to solve complex IT security issues and working together as an ecosystem above individual sort of competitive strengths and differentiation.
Yeah, and I totally agree with that. I think all the members of the consortium are of the belief that that bringing this technology to market, maturing it, evolving it, and continuing to expand on its capabilities is something that's going to benefit us all. It's not only good for the companies that are part of the consortium from a business sense, but it's really good for just the overall IT community to have a much higher level of security. If we're living in a world where, all data is at risk at all times, that is just not safe to use computing for anything because it could be breached, that's bad for the entire industry. And so by being able to bring confidential computing and proliferate it throughout the industry, that is good for the entire IT community.
That's great. And as far as standards go, the standards, I presume, are still evolving because this is so new. So is that something the consortium gets involved with? If I'm a user, a developer, and I'm concerned about doing something that's going to be in step with standards as they evolve, what do I need to think about? Any thoughts from either?
Yeah, so I think you're absolutely, standards are evolving. I think standards are going to emerge that will make it easier for relying parties to compare different implementations in the future and to determine which implementation is best for the risk profile, the threats, and the environment where someone's looking to run their code. in the future, it's possible certification schemes will also emerge to give buyers and auditors even more confidence in the implementations that they're looking to take advantage of. And I think, again, that's an area where I expect the Confidential Compute Consortium to be very involved.
Great.
Right. And I'm just to add to that, the standards give us all a platform for innovation. There has been a strain of thought in the world that standard commoditizes everybody, and I can, just working with ARM over the years, we don't believe that. What standards do is that they provide uniformity for users and a platform for innovation for which companies can build and innovate and ultimately differentiate. But standards in general accelerate innovation within an industry. They don't inhibit it.
Great. So before we wrap up, just one final thought from each of you. What should we do next? Where are we going? What thought would you like to leave us with? Mark, let's start with you.
Yeah, I think just look at the potential. Think about the applications that where you'd like to make your data work for you in different environments. Now, whether that's really taking advantage of the cloud so that you can start to share data, so you can train machine learning models with a greater wealth of data, whether that's thinking about the data that's currently locked away in a data center and you can't make it available to your mobile workforce or to your partners because of information security problems, and really some of the friction and the drag effect that information security can have on how you use data today. And how that can be different in the future as organizations are able to take advantage of confidential compute. I think the applications and the good that can come from it is almost limitless if you think about the potential use cases in areas like healthcare. So I think what I would certainly encourage people to do is think about the potential future where data is able to move about and go anywhere and really work for us without those traditional constraints, and then look to innovate to deliver on that dream.
All right.
And just one last thought on that one is that anytime you find yourself saying, we can't do that, and the answer is we can't do that because of data security, data privacy, data regulation, ask yourself whether or not, if that could be protected, could we go ahead and implement that? Could we do that new service? Could we do that new collaboration? Could we migrate that data to the cloud if we had assurance that that data would remain confidential? And I think if folks think about that will open up possibilities in confidential computing.
Great. Well, thank you to the two of you. I want to thank you both for being here, and thank you for the consortium for enabling this. And if you want to learn more about confidential computing, please go to confidentialcomputing.io. And you can find out a wealth of information there about confidential computing, about any questions that you might have. So thank you again for joining us. And thank you to Mark and Mike for your time in sharing your background with us.
All right.
Thank you.
Thanks,
Thank you.
Linda.